Cast is now starting. All attendees are in listen-only mode.
Today, our webinar is on evaporation and evapotranspiration, modeling this in GoldSim. This is part of the water management modeling series, where I will be presenting, not just me actually, me and others will be presenting weekly, every Thursday, both in the morning and in the late afternoon, to provide a time that is convenient for hopefully all of our customers around the world. And these will be going all the way through to the end of November. And each of these webinars will, for the most part, build on previous ones. So it will help if you are able to attend each of these. And if you cannot, we do record the presentation and post the video recording in our archive. So you can always go back if you need to. So today, like I said, we'll be talking about evaporation and evapotranspiration. These models that I'll be showing you, for the most part, are a function of temperature and possibly some other climate factors. But it might be that you don't need to use a model necessarily to calculate these. Perhaps you could just reference measured data. So I will talk about that as well. All right. So what we let's see. What I want to start with is a simple model. But before I go there, let me just talk a little bit about the data. So I'm going back to a website here. Now this is just an example. This is a site that's managed by a university in the state of Utah State University. It's a really good site, and they have a lot of information here. In particular, you can download evapotranspiration, like reference evapotranspiration. And if you're unfamiliar with that, just note that reference evapotranspiration can be used to derive the evapotranspiration or crop water requirement for specific crops. But it is kind of the baseline evapotranspiration that you can start with in order to calculate those kinds of things. But also you can calculate evaporation from a body of water, like a lake, if you need to, from that information. So what you can do is you can go to this website here, and you can see up here it's climate.usu.edu, and from here there is a way to browse various gauge stations, and you can look at the type, you can look at all the information about these different gauges, but when you click on it, it will take you to the data. Well, you have the option to go to the data, that is. If I click on it, then there are, oh, well, it was working earlier. Maybe I need to refresh the page. But anyway, maybe if I refresh the page, then it will bring up a link that says you can look at the full report, which was just what I did, and then it takes me here. The only reason I'm showing you this is just because sometimes you don't need to model this kind of thing. Sometimes you can just gather the data and then just reference the data. So for example, if we were looking at this, you can see it's formatted in a certain way that you can't just immediately start using in your model. You would have to format it in a certain way. But there is something here. You can download a CSV file, which you could save it as an Excel file and have it automatically imported into GoldSim. But probably best that you first review the information, make sure that it doesn't have any blank values or non-numeric values or numbers that don't work. But all this data looks pretty good. But you just need to format it, put it into a time series, for example, and then you could use it in your model this way. Now, we did in the two previous webinars, we talked about ways to take tabular data like this and then transform it, and also to interpolate values, like, for example, monthly values, which is what we have here. You can put these into a daily time step model, for example, by interpolating between these values in various ways, which we talked about in the previous two webinars. So I'm not going to go back and rehash all of that, but just note that if you can get evapotranspiration or evaporation data or pan evaporation data from online, and you're going to use that in your model, then just use the methods that we talked about before to take tabular data and for in whatever format that it's in, if you need to interpolate it, or if you're just going to use constants over the month, or however you want to do it, you can use the methods that we talked about previously. So I'm not going to spend time showing how you would do that here, just because it's the same. We'd be using the same methods that I showed you with precipitation, temperature, radiation, and wind data. So very similar. Okay, but I just wanted to show you that this kind of information is accessible online for various locations. All right, so with that, then you could do certain things like, for example, calculate the evaporation from a reservoir by looking at the evaporation from the water surface of the reservoir. Here's a simple pond evaporation model that you can get from our library. Now, just if you've not been to our library, just note it's our GoldSim Help Center. In here is a section called Model Library Applications. And then in here, it would be under hydrology. This is where you'll find anything related to evaporation, evapotranspiration. And we do have a few, like this one here, which I'll be showing you, and also this one. So, okay, so you can go here and when you click on these, you can download the model and use them as you might need. So the first model I want to show you is a pretty simple model called the Hammond Method. There's a reference here. If you double click this, it'll take you to a website that talks about the procedure. It's pretty simple. It's a method that is not based on the physical process, but is just empirical. There's a coefficient that you can apply. Don't get this K factor mixed up with crop coefficient, which is always denoted as Kc. It's just called a proportionality coefficient, which is by default 1. And so apparently you could perhaps make minor adjustments to this for calibration. It didn't talk about that a lot in the reference, but maybe you could go deeper into it and see. But what this model does is it calculates evaporation, and which can be applied to a body of water as long as it is not too shallow. If it's more shallow, then you might want to consider making an adjustment to it. But in addition to that, you can calculate evapotranspiration if you're looking at going into calculating, for example, water demands from certain types of crops. But this is a very simple method. And next I'll be showing you something that might be better if you're looking at calculating crop demands. But anyway, for just a simple method that you want to calculate evaporation, this might be a good one. But just note that the main inputs to this model, there are 3. You can see them up here at the top. We need the latitude of the site. The reason we need that is because this will take into account things like the position of the sun and the number of daylight hours, that kind of thing. But again, all empirical. But that is important. Also, the temperature, both max and min temperature. But as you can see, what we're doing with that is just taking the average. So you don't actually need min and max. You could just find average daily temperature to calculate. Also keep in mind that the methods that I'll be showing you today are all based on 1-day time step models. So if you're looking at something else, maybe something more detailed, then take that in consideration. But some of these models should be able to translate well to other time steps, well, in particular, smaller time steps than 1 day. But the data that I'm using is all 1-day time steps. For the most part, that's what a lot of these water management models that are built in GoldSim use, is just 1-day time steps. So that's why I'm focusing on that. Okay, so if you look at the equation for evaporation, you can see it's pretty simple here. But one thing I just want to make note of is all of these functions that I'll be showing you, for the most part, involve temperatures. And you have to be really careful with temperature data, or the temperature units in GoldSim. As you know, GoldSim is unit aware, so all of the unit conversions are taking place for you in here. But with temperature, you have to be a little bit careful, because there is a big difference between the temperature as a value versus temperature as a change, or as a difference. And what I mean by that is, if you're trying to calculate let's say, for example, the change in temperature over time, then that is a difference in temperature, and that requires a totally different type of unit. And so let me just show you that difference. Let me just go to edit mode, and I'm just going to create just a dummy expression here. But let's say we have temperature Celsius right here, and I say, let's see, let's just say 20, like that. Okay. So if you're going to have a change, if you want to calculate the change in temperature, the difference, then what you actually want to use is CDEG, like that, Celsius degrees. And you'll see here that that is not converted to Celsius, as you might have expected. It shows a very large number, and so that is something to keep in mind here. You could have a conversion problem if you are not understanding the difference between these, or when you might need one versus the other. So just as a rule of thumb, if you ever are looking at a difference in temperature between maybe two different temperatures, or if you're looking at a change in temperature, then you want to use the unit CDEG or FDEG. As an alternative to this, you could work in absolute. You could work with Kelvin, and then you don't have to worry about this different type of unit. Another option is to just cast the units off and work with just unitless values, with an assumption that they are a certain a unit, and then at the end of your calculation, perhaps put the unit back on. So in some cases that's necessary, which I will show you. In some cases it's necessary because you might be working with an empirical equation that might raise something to the power, not to an integer power, for example, in which you could not use units anyway, and so you'd have to cast them off. So just be careful with units, and you will see equations that sometimes look like this, where you have a 273.3 in there. That kind of thing usually indicates that well, actually, that's not the exact number I'm thinking of. Let me back out of that again, and I'll show you an example later where the value is actually intended to be in Kelvin, and it would be adding a number like that. But anyway, just keep that in mind, that you need to be careful with the use of temperature units. And we do have in our help documentation a discussion of that difference, which, by the way, you can always go to our help documentation just by clicking on help here, or click on the question mark button up there, and that will open our help system. Okay, so with this, we run this model, look at the plot, then you can see here evaporation. Well, in this case, we have evaporation, and that is also compared to ET, evapotranspiration. And you can see that it is that ET is slightly less than the lake evaporation. And if you were to, if you had also, for example, if you had a pan coefficient, then that would also be slightly different here, and you'd have to use some sort of parameter to convert between pan coefficient and, or sorry, pan evaporation and lake evaporation. I'll show you that in another model here, but you can see here that it is derived from temperature, because the red line showing temperature, you can see even though they're not aligned, but you can see that the changes are reflected in the evaporation rates. Okay, so this model would be might be useful if you're just trying to get ballpark numbers for evaporation, in which case your model might not be very sensitive to evaporation. If, however, your model is very sensitive to evaporation, then you might want to consider using a different approach. Because again, this is just an estimate. But let's look at how some of these simpler models might compare to measured data. So a similar model, a similar one to this. Let's see if I already have it open. Nope. Okay. So a similar one to this is called Hargreaves Samani. And in this case, I put in another element here so that we can use Monte Carlo simulation to sample the temperature time series. So if we look at the temperature here in this model, it's measured temperature from 1894 all the way through 2020. So it's a lot of information. Also, you can see that these values might look kind of strange. The reason for this is because the values were converted from Fahrenheit, and it was done immediately after pasting the values. So for example, if I put in, instead of Celsius, I put Fahrenheit here, and then go back to edit data, then you can see these values were automatically converted to Fahrenheit. So these are the values that were probably posted or downloaded from the web. In some cases, there's going to be a slight numerical error here. So you can see this was probably 54 when it came in. But all of these things can be taken care of simply if you first convert them before bringing them into GoldSim. But this really is not going to make any significant difference, obviously, to the result. But I'm going to put this back into Celsius, so you can see that when it's in Celsius, now converted again. Okay, so we have Tmax and Tmin, quite a bit of data. We have enough data, in fact, that we could run many realizations and sample and get a good sampling of the entire time series, which is what we were doing in this model. So if I go to simulation settings, you can see it's just running an arbitrary year, in this case, the future. And then we go to Monte Carlo, and you can see it's running 71 realizations. But in our case, because we have, let me just check again when the start date. And so we can just check this. We could say, let's see, 18. Instead of doing the math in my head, I'm saying, let's see, 2020 minus 1890. Was it 1894? I can't even remember. 126. So 1894. Okay, so about 126. I'm going to say 125 realizations. That's how many years we have of record there. So we could run this model for 125 realizations, in which each realization represents a historic year. We could run more realizations, but that just means it's going to repeat or copy. It's going to resample the same year that it's sampled before. So, which is it could be fine in this case. But the shift year is the key here. So what we do is we say, I want to incrementally walk through the historic record of temperature starting in 1948, but we don't actually need to do that. We could say 1894, and then add to that the realization, which always is just a counter starting with 1. So you can see we have -1, so it's starting with +0. That'll start us in 1894. And then on the next realization, when this is 2, it'll be 1895, and so on. As you increment through all of the realizations in this model. I'm just going to move this a little bit here. Okay, so with that, and I talked about time shifting in the previous webinars, but you can see the shift year is put there. And the reason we use this element here is because then we can apply that to all of our time series throughout the model, and so that they're all aligned. And that's what we want. We want all of our time series to be sampled incrementally, starting with the first year and then walking subsequently through as we go through each realization. Then as we do that, again, we also need the latitude of the site. And with that value, then we can calculate the radiation. And from that, calculate reference ET. From that, and so you can see this is a little bit more detailed than the previous model I just showed you. The previous model did not have a calculation of radiation, so a little bit different. But as you work your way down through, you can see that we end up with applying a crop coefficient in which you can then calculate evapotranspiration for a specific plant or crop. But you can also just back calculate the pan evapotranspiration if you wanted to. In this case, I'm only doing it as a check. Now we could just apply that to the reference ET, obviously, but I have a KC value of 1, so it doesn't matter. I could apply it to evapotranspiration over there, and that'd be just fine. Anyway, what I have here is for this particular site, I have measured pan evaporation data for a particular location. And now what I want to do is I want to essentially simulate the same output and then compare it. So if we run this model, then look at a plot, then this is just looking at one possibility, one realization. You can see down here red is simulated, green is the measured. So the green is not changing in any of the realizations. It's just monthly measured evaporation. And so we can flip through some of these realizations and see how the simulated values are jumping up and down all over the place. And it's really just because it is a function of the temperature. This general curve, the shape that we see in the red line, is a function of the site's latitude. If I change this from realization to a statistic, then you can see the comparison of how our simulated values on average relate to the measured evaporation rates. So it looks like it's a pretty good fit. We would expect the values to kind of go through the center points of these lines, and it's doing a pretty good job of that. It might need to spike a little bit more in July to match a little better, and also it might be going up a little fast here at the beginning of the year, but other than that, it looks pretty good. And so you can see this method, at least for this site, under these assumptions, seems to work pretty well. So if you're trying to calculate, for example, evaporation on a water surface of a lake, then this might be a good method. Also, if you're looking at doing some simple calculations for a water balance that involves irrigating crops, then this might work too for that. You can also see we have some links here for documentation of this method and also a case study if you wanted to compare. This model is available on our website, I'm pretty sure. I think we saw that on there. There it is. So if you go here, then you can read about it and also download the model and put it in. Okay, so just an empirical method that is fairly straightforward, not requiring a lot of data, just temperature, but in this case, not average temperature. It does require daily min and max temperatures, but that information should be pretty easy to obtain, maybe not for your exact site, but maybe a location nearby, but still pretty straightforward as far as gathering that kind of information. Okay, the next model I want to show you goes a bit deeper, and this is a well-known method. So let me just close this. Okay, and this background picture is pretty spot on for what's going on in Seattle right now with all of the smoke that we have. So I've been stuck, not only because of pandemic, stuck in the house, but also stuck more because of the smoke. So it's been quite a week. All right. So the first thing I want to show you is calculating reference evapotranspiration using the FAO methodology. And I have a link here. This is a pretty famous methodology, and there's really good documentation for it. This method uses more of a physical approach, and I'll walk through some of those calculations here in a bit. But if you're going to use this, then I highly recommend that you look at the documentation. It's really well written and very thorough. So here it is, and the entire document is online. You can just browse through all of the different components and read about them. And this is how the model was built. Actually, was reading this very good documentation, walking through it, and putting the equations in. Okay, so with that, then you can see here that this model uses a bit more data. So again, daily min and max temperature. Oh, also it's a 1 day time step again. Daily min max temperature, but it also requires, in addition to that, well, latitude like we had before, but the elevation of the location, and the duration of sun on for each day, and also the wind speed. So if you were in our previous 2 webinars, we talked about, well, not previous to the last week's webinar, we talked about modeling temperature, radiation, wind speed. And so you can imagine how with a wind speed model, for example, you could replace these constant monthly values with a wind model, like we talked about last week. You could also you could swap out these time series with simulated temperatures. If we have time after I present this, I will show you actually what it would look like if you replaced those with models instead of having these as input data. Okay, so with that, then what we do with these is we have these other containers. So for example, air temperature data, we take those values. There's not much going on here. We just calculate the mean, but keep in mind we do use all 3 of these. We use min, max, and mean for the calculations. For wind speed, we do a bit more. In this case, I am doing interpolation between monthly values because we don't necessarily want to have we have a 1 day time step and we have monthly values. So sometimes it's okay just to have a constant for the month and then jump to the next value on the next month. But if the jumps are great, if they're significant, so for example, in this case, we have a jump from 6.2 to 7.9, 8.3, and then 10. Some of those jumps might have a just on that one day as you transition from one month to the next, they might have a kind of an effect that you see all the way downstream in your model that might cause the model to do some weird things. For example, a sharp spike in something, a flow, for example, and it's not real, right? It's all just driven based on the way that you've interpolated the data. So sometimes you want to avoid these sharp jumps on a one-day time step like this if you're using monthly data, and you can easily do that with either linear or spline interpolation of the data, which is what I'm doing here. I have an interpolation that if we run the model, actually I need to run the model just for one realization to show you. I'm just going to pick a random year, realization 50. So if I run this, then what you end up with is something that is not jumping immediately. It's smooth over time. That's using spline interpolation. But wind in this model is not a major contributor. It's a small contributor. The model is not very sensitive to wind speed, so I wouldn't worry too much about that one. It's more sensitive to the temperature, the latitude, which you'll see. Okay, so the next thing we calculate after temperature is air humidity. So if I go in there, then here are the calculations, and all of these, well, not all of them, a lot of them are documented using the note pane. So if you've not used the note pane, you can see it by clicking on this icon here, and then the note pane will open, and you can dock this note pane in various places. I like to have it on the right because my screen is wider than tall, but you can move this, just go up here to the top and drag it, wherever. You can move it down here, or you can just have it floating if you want. But anyway, if you see an element that has a hyperlink like this in the ID, then you click it and it will show you more about that that element. Also note that the note pane is formatted text, so you can have italic, different fonts, bold, etc. These things can be just copied and pasted from a Word document, for example. In my case, some of these are copied from the actual documentation, the FAO documentation. Okay, so we work through these equations and we come up with this thing called ES right here, mean surface vapor pressure, which is used, actually some of these, this thing's used as well, the slope of saturation vapor pressure. But you can see some of these units, and this is the one I was talking about. This 237.3 is a conversion factor from Kelvin, and so you'll see those numbers sometimes. Just keep in mind that's what it's for. But the units in this model are very important. And so, yeah, sorry, I was just showing you that. Kilopascals, for example. Note the kilopascals here. Goldsim has to know what those are. It does. And so it's nice, I think, in this model that we don't have to worry too much about the units. That you will see some places in some empirical functions or calculations, not empirical, they're unitless equations because they're using some power functions, and so we have to cast some units out in some places. But for the most part, it's very straightforward in doing these calculations. We don't have to worry about unit conversions anywhere in here, so that's really nice. The next thing after humidity is solar radiation, and again, that uses these three inputs in addition to the humidity and temperature to calculate that. And again, this is using the FAO methodology. And I think somewhere in here I've got oh yeah, so right here, I just copied and pasted from the FAO documentation, which is nice. You can do in GoldSim, put in some graphics to help with looking at some of these element names that are used. I used all the same naming that the documentation uses, and you can see that the documentation is pasted over here. But there are a lot of calculations going on in here, and so one other option instead of doing it this way might have been to use a script element, but I kind of like the way that this is formatted because it allows me to more easily debug the model. If I wanted to, for example, actually this did happen. I was getting an output. Let me go to the verification plot here. So this is showing the predicted ET for this one realization as it corresponds to the measured ET, reference ET. In fact, maybe I should first show you the daily. So this is daily, and you can see it matches okay. Maybe on the falling limb, it's not the best, but it's pretty good, I would say. But before, I was not getting a very good match at all, and I had to go and debug the model and find out what was wrong. And it was very nice that I could plot each of these outputs and compare it to a case study in the documentation, and it led me to the problem actually, and it turned out it was over here was the problem. I was linking to T min instead of T mean, and you can see the name is very close there, and that was the problem. And so I was using the min daily temperature instead of the mean. But anyway, so you could do things like, you know, zero in on specific components of these functions and see what they are, and read the documentation and see how they compare and so forth. So that really helped to do that. But anyway, all of these names, they might seem kind of strange, but essentially what they're doing is they're taking components of these massive equations and just kind of breaking them down. You know, if you need to see individual parts of the equations, so that did actually help a lot. There's another graphic that's put in. So okay. Anyway, all of these then come together in one place where you add them up. There was a condition where I might have had a negative number in some small isolated times of the year, mostly in the winter. No, not mostly, only in the winter, where we might get a negative. So we have to guard against negatives. We don't want that. So I had to make sure we did never drop below 0 with this max function. And that's the resulting reference ET right there. And that reference ET then can be used however you wish in your models. And so the nice thing about GoldSim is that you can compartmentalize all of these types of functions and reuse them however you wish. And so I wanted to demonstrate how we might do that in a real model. So let's just say, for example, we start a brand new model in which we want to calculate the let's say crop demands or water demands to irrigate something. We do have another model that you can get from our website. That one is, oh, I don't have it open at the moment, so let me open that. Here we go. Irrigation water demand for crops. So this one, again, you can get this from our library. What it does is it requires one major input, reference ET, which we just talked about. Right now it's just a constant, but what you would do is you would replace this value of 1 inch per day with the output of the previous model we were just looking at. And the main drivers in this model are the times of year in which you have different stages of irrigation for various crops. And so it's important in this model that we have an array label set called crops. And you would then immediately, when you use this model, you would, you know, obviously put the mix of crops that you're working with. Maybe it's just one, maybe it's a whole series of them, but you would list those here. And then in the crop curve here, this is where you put the data. So again, this is all based on, you can go to the FAO documentation and look up how various crops have different coefficients as it goes through the season, the irrigation season. Typically, they have an initial, mid, and end coefficient that's changing. So in this case, we have it the initial KC for the different crops. You can see it's a vector of crops, and here are the KC values for the different crops there for initial. This is the startup of irrigation, and then the mid. These are always going to be, well, most always would be higher. This is probably in the middle of the growing season. And then you have the end. So toward the end, toward harvest time, is when you'd have those factors. And you might have intermediate or more factors in that, and that's fine. You can add them, but you'd have to make sure you incorporate them correctly and time them correctly. So the timing is important. Now I have planting dates here as an example, but there are other dates here. I'm just going to show the planting date. These dates are actually the Julian day, so the day of the year. That's just the way that the model's set up. But you could, if you wanted to do this in a different way, no problem. You could set this up, for example, you could specify a month and a day of the month if that's easier, but you just have to modify the function that's using this a little bit. But it could certainly be done that way. I just thought this is easy. This is how the FAO documentation is using it. And so I think it's how it's using it. I need to go back and look, but pretty sure this is how it's using it. Now, this is one area that I don't have it as set as a stochastic, but it would probably be useful to do that. Or you could model the day that it needs to start based on the temperatures leading up to this day. So, and rainfall too, by the way. So for example, you could have a model that says, that's watching the temperature leading up to day 91, which I think is like somewhere in April. You could model the temperature, and if it's rising faster than a normal year, then you would move this day forward. You would move it to a smaller number, right? You'd move it forward, or wait, I guess that's backward in time, maybe into late March, for example. And so you could calculate this number. You could have it be a function of temperature and rain. So if it's getting hotter and drier faster, then make that number smaller. If it is still raining and it's still cool, then perhaps you make the number slightly larger. That kind of thing could be done, but it's not in this model, and it is reflected. You will see a pretty big impact to this number being a constant. Let me show you what I mean. If I run this model, then we come down here. Oh, we might not actually. Okay, we're not going to see it yet, but you will next when I incorporate some uncertainty in here. But these lines that are jumping here, these are the functions of the initial, the middle, and the ending irrigation season. And so the initial is going to be leading up to the point that you see this flat line here, and then the mid is this flat line up here, and then the ending is over here. And there's always going to be a, oh no, I'm sorry, the end I think is this point here, and then in between the points, GoldSim just interpolates linearly. That's the assumption, that it just interpolates linearly up until it gets from the initial to the mid. So that's just pretty easy way to transition there. Now, of course, you could do more fancy things here. Instead of just assuming it's a hard break point between these, you could do a more of like a spline or something if you wanted between those to make it a little more realistic. But I think that's probably not going to give you a lot of benefit. I think the bigger benefit would be to derive these transition points in the model instead of hard coding them. Okay, but let's just pretend like we have a model where we want to combine the two, the evapotranspiration and this model, into one. Okay, so let's go ahead and do that. I'm going to start a new model. And we will just initially set this up to be a hypothetical calendar year that starts in 2021. And we'll go for one whole year like that. Please keep in mind that even though this says it's ending in the following year, it's actually not, because it's midnight. So it doesn't advance at all into 2022, even though it might appear to you that way. It's not. It's ending at midnight. So this is how we want it. The next thing we want to make sure is that we're running Monte Carlo, and we are for just one realization. That's fine for now. This is always a good idea when you're building a model to keep things simple. It might be tempting to run it for many years right off the bat, because that's how you want the model to end up. but I recommend not doing that for complicated models like this. I recommend staying simple. Just 1 year is fine, because that gives us a really good idea of how the seasonality is affecting the model. Okay, so this is running for 1 year. Now what I want to do is I want to import the ETO calcs is what I'll call it. Okay, so I'm going back to that model, the reference ET, this one right here, and I just want to select all. So that's Control A and then Control C to copy. That's all copied. Now I go back into here and then go into this container. So you see that I just click on the navigate into, and then just click here in the upper left corner and Control V to paste, and then we have it all in here. So now I go up a level. You can see that this model browser has now changed with a way to expand. You can see all the information in there. So that's this one. There is a chance that I have some duplicate names, so it'd probably be a good idea to localize this container so that all those names are local in there. All right, next one is going to be the crop demands. Again, I'll localize it, and I will go in there, and I want to paste into here. So I go back to that other model that calculates the crop demands, Control A, Control C, back, upper left corner, paste. Okay, a good thing to do is to hit the F9 key, which is the equivalent of going up here to Model, Update Expressions. When you're doing big copy paste like this, it's probably a good idea to do that just to make sure everything is good. And GoldSim has parsed everything and is happy with all the connections still. Now what we need to do is connect these two, because in this model, if I go in, you see I have this ETO input right here that's currently set as a constant, but I want to link that. I go up and over to ET calcs. I want to link it to this one, reference ET. So the easiest way to do that is probably just to go back, browsing back using this browser button here, open up the expression and just wipe that out, right click, insert link. Now we just need to browse in the model to the ET calcs and find the reference ET. There it is. Click OK, and it's going to say, oh, I need to expose this on the container called ETO calcs. That's great. That's exactly what we want to do. Puts that in, and now you see we have reference ET in the model, and now we can calculate the crop ETs. Now this is going to be a vector. We're calculating the crop ETs for all of the different crops there. Somebody asked, for areas with snow, how do you typically handle it? Getting the pan evapotranspiration when the snow is on the ground. That is a good question. Now, I think one of our next presentations will involve snow melt and snow accumulation. I wonder if we'll be talking about that. No, probably not in regards to crops and crop demands. So that is a good question. I'm also avoiding precipitation, because this, if you're trying to calculate water demands right here, then you would want to take into consideration the what's called effective precipitation. And I think that's perhaps where this could come into play as far as snow goes. Maybe it's similar, but the thing you have to keep in mind about effective precipitation is that it's the total precip, right? Which we can model. We talked about that 2 weeks ago. You could incorporate that in here, but you have to remove the amount that's evaporated. You have to remove the amount that runs off, and you have to remove the amount that's lost to deep percolation, because whatever's left is what the crops could then use in the root zone there. I'm trying to think if there's anything else that would, you might have some ponded water on the surface that also evaporates later. So anyway, there's some losses, right? You end up with effective precip. And so I think with snow, maybe we could do the same thing, but that's different, right? Because it's covering in a different way than rainfall. So I don't currently have anything in this model that deals with snow So that should be something to consider. If snow is something that's a major factor in your model, that would be considered. But I think we could look at that downstream of this point, because that's what we're going to do with precip. Calculate effective precip after this point. Right now we're just looking at what is the crop demand, irregardless at this point of precip. Okay, yeah. Okay, so in regards to snow, let's do kind of hold that off until we talk about snow accumulation and snow melt in a following presentation. But that is a good question. Thank you for asking there. Okay, so so what we do now is we should see some impact of the reference ET. So if I go back over here to ET crop, you can see it now looks very different. You can see that we have the jumping up and down due to the temperature that we saw before, but we also have this very fast rise in water demand. Okay, now this is just evapotranspiration, but we can look at the actual water demands. Are these being plotted? Let's see. Oh, okay. I don't think they're being plotted, but anyway, so this is the total water demand for all the sum of all of the crops. But you can see there's kind of a bigger spike going on right here, and that's because of the demand on the crop itself, and the way that it ramps up. But here's what I wanted to show you. If we run this for multiple realizations now, let's go ahead and do that. So I'll just run this for whatever we had before. I think we had, what was it, 125? When you change to multiple realizations, you always get this little note that says, oh, hey, by the way, everything in your model is not going to be saving results anymore, unless it's connected to a time history results element. So this is important. Maybe you get annoyed with this little message and just always click it away, but just keep in mind that's what's happening. We don't want to save results in every single element, because running multiple realizations requires saving a lot of data. Now we're multiplying everything that we were saving. We're multiplying by 125. So we don't save by default anymore in all the elements. That means it's harder to debug the model. So that's why I'm saying at the beginning, when you're building your model, always just do it for one realization. So you can easily walk around. You can right click on any element and see its outputs immediately. Then when you're ready to move forward, then you could run it for Monte Carlo. So here now we're running it for multiple realizations, and I have a problem because one of my, I forgot there was a time series here that I had. Oh, this is a different model. That's right. I don't have the same number of realizations that I don't have the same number of years available in this model as what I had in the previous one. I think this one might only have maybe 70. I'll just put 69 just to make sure that I can run it. Let's see if that works. Okay, so that's good. This model just doesn't have enough years. It doesn't have 125 years. It only has 70 years. So that's why I did it that way. But this is what I wanted to show you. If I run this model and then I look at a statistic, for example, you can see that there's this kind of odd looking straight line on the mean. Also probabilities. Alfalfa doesn't look that strange, but this one, well, yeah, see right here, that's and especially the wheat. So this is not very realistic. You're not always going to end irrigation exactly on the same day, right? It'll adjust depending on the situation, depending on the temperature and rainfall. So although I guess there might be some exceptions there. Maybe there's some law or something, or you just have to end on that day all the time. Okay, that's fine. But for the most part, I would say this is not very realistic. So that's why at the beginning I was talking about how these dates that you put in, the planting date, for example, the final stage date, those dates probably need to be have some uncertainty applied to them, or they need to be calculated as a function of your climate inputs. If it were me, I would probably make them a function of the climate inputs, because just having them totally random might also not be might not be realistic, but that would be something that you could look at adding to the model to get that. Okay, so now as you've probably been noticing, these models are all driven by temperature. So one more thing that we could do here, and I'm kind of out of time, but I just wanted to make a note of it. You could add to this model, for example, WGen, which is what we talked about in the last two presentations. And if we add that, then what you can see here is we could replace temperature. We also have that wind model we talked about last week. We could replace that here. And so all of the inputs can still be aligned with each other. And they can also provide more realistic projections into the future, showing all the different possibilities that you could have, that still would be reasonable based on historic data, because as you know, the WGen model, the parameters are derived from historic records. So it's not just totally random, but it could still provide you with a good range of possibilities. And in addition to that, allow you to make systematic changes to climate inputs to account for things like climate change, for example. If you wanted to run a very long forecast, multiple years going forward, then you could adjust by year things like average temperature, for example, or the variability in the temperature, those kinds of things, to see how that might impact your water demand, or your lake evaporation, for example. Okay, so I'm out of time, but just keep in mind that all of these models we've been talking about can be connected, very easily interconnected, as I've shown you here with this. All right, so that concludes the presentation. If you have any questions, I will wait around to answer them. Somebody said, I had a problem with the Hargreaves Samani model to use it in high latitudes above the Arctic Circle because the sun doesn't shine all the time of the year. Any solution? Can I just put radiation to 0 on those days? That is a good question, and I have no idea. I'm sorry. I've never used it in that case. I wonder if you could employ perhaps this model, the FAO model. And the reason I say that is because it's a bit more robust. I might recommend going to this, even though it's a more complicated model. It's well documented, and perhaps you could find maybe you would find that it applies better for that. So you can get this from our website. I might recommend going to this model and trying it out for that location. I'm just not I'm not well versed in that model, particularly in an area like that. So I might recommend that you try this approach and see how this works for you. But yeah, you did say maybe put the radiation to 0 for those months. Maybe, but the radiation, does it require radiation in that model? I forgot. Let me open that up again. Sorry, I'm just going back and finding that. Oh, that's right. Yeah, so you're saying override. You're saying override this number with 0 during those months, or a lower number. Yeah, maybe. Um, hmm. I wonder if there are other factors that, in your case, that are affecting it. So you must mean that your ET numbers are higher than what is expected or reasonable during the winter months. Um, maybe could you tell me what the latitude is that you're working with? I'd be interested to just see what answer I get right now. If you can tell me what the latitude is of your site. Another question is, Hargreaves Samani could not be used because of the assumption that the assumption is that the solar radiation should have positive correlation with temperature. Oh, good point. Okay, thank you for bringing that up. Um, Interesting. So maybe this is not a good model for that location. Um, why don't you try using the FAO method and see if that helps. All right. Any other questions? I'll just wait around for a couple more minutes in case you're typing a question.